Welcome to part 2 of our simulation series, focusing on Newton's second law, velocity-Verlet, and validation. This lecture expands on force-based simulations. We will be using the velocity-Verlet algorithm to explore simple harmonic motion, projectile motion, and uniform circular motion, ending with some dynamic animations of these concepts. By the end of this session, you should be able to clearly distinguish between kinematic and equation of motion simulations. We will derive acceleration from force using Newton's second law and implement the velocity-Verlet update equations to build our physical models. You will also learn to employ crucial diagnostics like energy conservation and time-step convergence to validate your results. This initial code block sets up our environment, importing essential libraries like NumPy for numerical operations, Matplotlib for our visualizations, and IPython's display tools to help with animations. The output confirms our libraries are ready. Note that we have animation rendering turned off by default to ensure the notebook executes quickly when you run it. Let us briefly recap Part 1. Previously, we used known kinematic formulas to visualize motion. However, simulating motion directly from the equation of motion, F equals ma, is a more powerful and general approach. This allows us to compute acceleration directly from the acting forces, updating position and velocity step by step, rather than relying on a predefined trajectory. To step our simulations forward in time, we will use the velocity-Verlet algorithm. Unlike the ordinary or leapfrog-Verlet methods, the velocity-Verlet algorithm is particularly useful because it provides both the position and velocity explicitly at each time step. For one-dimensional motion, the update equations show that the new position depends on the current position, velocity, and acceleration. The global error in both position and velocity for the velocity-Verlet method is approximately proportional to the square of the time step, written as big O of dt squared. This error scaling is a critical factor we will be monitoring to ensure our simulation remains accurate. Here, we define a Python function to integrate one-dimensional motion using the velocity-Verlet method. The function takes the acceleration function, initial conditions, the time step, and the final time as arguments, and uses a loop to systematically update the position, acceleration, and velocity arrays. The output here simply confirms that our one-dimensional velocity-Verlet function has been successfully defined and is ready for use in our upcoming examples. Our first source-preserved example applies this algorithm to a simple harmonic oscillator, like a mass on a spring. Using Hooke's law, F equals minus kx, Newton's second law gives us an acceleration of minus omega squared x. We use this because we have a known analytical solution involving a cosine function, providing a perfect baseline to validate our numerical results. This code block sets up our physical constants for the simple harmonic oscillator and defines the specific acceleration function. We then call our velocity-Verlet function, calculate the exact analytical solution for comparison, and prepare a plot to visualize how closely our simulation matches the exact trajectory. This plot overlays our numerical velocity-Verlet result with the exact analytical solution. As you can see, the two curves match extremely well over multiple periods, confirming that our numerical method is accurately simulating the simple harmonic motion. This code block creates a phase-space trajectory, plotting velocity against position. This is another crucial diagnostic tool that helps us understand the dynamics of the oscillator. The resulting phase-space plot shows a closed elliptical loop. This closed loop is a classic signature of simple harmonic motion and indicates that energy is being conserved in our simulation, giving us further confidence in our model. Finally, we calculate and print the maximum error between our numerical position and the exact analytical position. The output confirms a very small maximum position error, on the order of 10 to the minus 3 meters. This quantitative check validates that our chosen time step is appropriate for the period of the oscillator. We will now use a func animation object to create a dynamic visual representation of the simple harmonic oscillator. This code defines the animation function, setting up the figure, the moving mass, and the spring line. It uses an update function to change the position of these elements for each frame based on our simulated data. This slide shows the HTML output interface for the animation, which provides slider controls to play, pause, and adjust the playback speed, allowing you to carefully review the simulated motion. Moving to 2 dimensions, our next example is projectile motion. When we apply gravity as the only force, the acceleration is simply minus g in the y directions. We will see how velocity Verlet handles this constant acceleration case. Because projectile motion is 2-dimensional, we define a new, generalized velocity Verlet function that can handle multi-dimensional arrays for position, velocity, and acceleration. The core update logic remains exactly the same, but it now operates on these arrays. The output confirms our multi-dimensional velocity Verlet function is ready to use. Here we set up the parameters for our projectile, an initial velocity of 50 meters per second at a 45-degree angle. We define the acceleration function to reflect constant gravity in the vertical direction and call our new 2D velocity Verlet solver. This code block plots the simulated projectile trajectory alongside the exact analytical parabola, allowing us to visually verify the accuracy of the 2D simulation. The plot clearly shows our velocity Verlet simulation perfectly tracking the expected parabolic path of the projectile. Since the acceleration is constant, the velocity Verlet algorithm is actually exact for this specific case. To calculate the simulated range, we look for where the y position crosses 0. We interpolate between the final 2 steps before hitting the ground to get a precise landing coordinate. The output shows our simulated range is extremely close to the theoretical range, with an error on the order of 10 to the minus 14 meters. This microscopic error is essentially just floating point noise, further confirming the algorithm is exact for constant acceleration. Now we set up an animation for the projectile motion, creating a figure with the calculated bounds and an update function to advance the projectile's position frame by frame. This code block executes the animation, linking the update function to the simulated position data to generate the dynamic visual. Once again, we have the HTML controls for our animation. In the live notebook, this will display the projectile moving along its parabolic arc. Our final example is uniform circular motion. Imagine a planet orbiting a star or a ball on a string. Here the force is directed towards the center, so the acceleration is minus omega squared times the position vector r. This is a very sensitive test for numerical algorithms. We set the radius and angular velocity to 1 for simplicity, giving an acceleration function that simply returns the negative of the position vector. We run the 2D velocity Verlet solver and prepare to calculate the exact circular path. This code block calculates the distance of the simulated object from the origin at every time step. For perfect circular motion, this radius should remain constant. Looking at the plot, we see that the simulated trajectory is indeed a circle. However, closer inspection is needed to ensure the radius is not slowly drifting, a common issue in numerical integration of circular orbits. To check for this drift, we plot the calculated radius over time. This plot reveals that the radius is not perfectly constant. It oscillates slightly around the exact value of 1.0. This oscillation indicates a bounded error in our simulation, meaning the planet will not spiral away, but the orbit is not perfectly precise. We define an animation to visualize this circular motion, creating the figure and the update function necessary to render the orbiting object. This code block finalizes the animation setup, attaching our circular motion data to the animation framework. Here are the controls for the circular motion animation, which will clearly demonstrate the object moving around the central point when rendered. The small oscillations in the radius plot suggest we need more rigorous diagnostics. A robust simulation should be verified using plots, unit checks, conservation laws, and convergence tests to ensure physical accuracy. Since the force is conservative, the total mechanical energy should remain constant, We can calculate the kinetic and potential energy at each step to verify this. This code defines a function to calculate the energy for our simple harmonic oscillator based on its mass, spring constant, position, and velocity arrays. The output confirms our SHO energy diagnostic function is ready. We run the diagnostic function on our previous SHO data and plot the total, kinetic, and potential energies over time to visualize energy transfer and conservation. The plot shows kinetic and potential energy oscillating as expected, while the total energy line remains perfectly flat. This confirms that the velocity-Verlet algorithm conserves energy for the simple harmonic oscillator. We apply the same energy diagnostic approach to our circular motion example. The kinetic energy depends on the velocity squared, and the potential energy depends on the radius squared. This code calculates the energies for the circular motion simulation and prepares the plot to examine its energy conservation. Here, we see that the total energy is not perfectly constant, but exhibits small oscillations similar to the radius error we saw earlier. While not perfect, the error is bounded, which is a key stability feature of the velocity-Verlet algorithm for these types of orbits. A critical diagnostic is the convergence test. We stated earlier that the global error scales as dt squared. We can verify this empirically by running the simulation with progressively smaller time steps and analyzing how the error decreases. This code defines a function to run the circular motion simulation for different time steps, calculating and storing the maximum error in the radius for each run. The output confirms our convergence test function is defined and ready to execute. We define an array of decreasing time steps and run our convergence test. We then prepare a log-log plot to visualize the relationship between the time step and the resulting error. The log-log plot shows a straight line with a positive slope. This linear relationship on a log-log scale confirms that the error follows a power law relative to the time step. To quantify this relationship, we calculate the slope of the line on the log-log plot using the polyfit function. This slope represents the order of convergence. The output shows a slope of approximately 2.0. This empirically verifies our earlier theoretical statement. The global error of the velocity-Verlet algorithm indeed scales as dt squared. For some guided practice, observe the relationship between the time step and the radius error. Notice how halving the time step significantly reduces the error. Looking at the output, when the time step dt is halved from 0.08 to 0.04, the error decreases by a factor of 4. This directly demonstrates the dt squared error scaling in action. To summarize, we have explored force-based simulation using Newton's second law and the velocity-Verlet algorithm. We successfully simulated simple harmonic, projectile, and uniform circular motion. Most importantly, we learned that a running simulation is not necessarily correct. It must be rigorously checked using diagnostics like energy conservation and time step convergence.